So I'll just start with a picture of, wait a second, a picture of Cambi as a motivation to explain my current train of thoughts in my mind. We are very worried in Italy about this particular system because it shows a lot of inflation and we still not understand the system very much. And so I've given a lot of thought of how to forecast eruptions. And recently, before it was more like a theoretical question. How can you forecast where a dike will go? How can you forecast the velocity of the dike? It was very theoretical. But then when this crisis started, I started to think more precisely what it would take to really forecast the propagation of a dike, where it will land, how fast will it propagate really, not just from a theoretical point of view, like applied. And then I thought that, so maybe some of you knows that I've been working with my students on theoretical models of dike propagation. We have done 3D models where the dikes can twist and turn, and we have also done simple models to have them run faster for rapid assessment. But then when confronted with this question, how would you really forecast a real eruption? I started to realize that we really missed a lot of pieces for the propagation models to really give you a reliable answer. For example, these particular models, which are 3D, and they are good because you need a complex path. You need to be able to simulate a complex pathway that real magma takes. They assume an invested fluids inside. And while there is now 2D models with fluid and pathway by Severin Forst, Virginie Pinel, and Francesco Maccaferri, there are still none that can have a fluid within a 3D propagation. Plus, real magma, like maybe basaltic magmas in Iceland, so the model would be adequate to address such a system because basaltic magmas are easier from a propagation point of view. But what about Campi Flegrei? So the magma is not basaltic. It would develop a lot of gas. It would develop a different viscosity as it was ascending due to the gassing, crystallization, change in buoyancy, change in density, change in viscosity. And how would a model really consider this to give a reliable time of propagation? And then I thought, okay, the properties of the magma need to be taken into account. And so now I'm taking a very long, a very wide perspective on this. I started to work on how pathways of dikes affect magma properties, and to later focus on how magma properties also focus on the affect the pathways and modify the propagation dynamics. So today I will tell you about, I will not talk about my propagation models, they are already published, but I will tell you how I think that pathways of magma by diking, so how diking, magma transported by diking, is how the pathways affect the magma inside the dike. So we know that magma plumbing systems need to be formed by a very complex system of dominated by crystal mass with some melt lenses, because this is required by the petrology of the rocks that we recover at the surface, and it's also required by the geophysical data that we acquire from volcanoes. Before I go to the questions that I want to answer today, I just specify that I will be talking sometimes about interconnected systems. This is some jargon, geochemical jargon that I learned recently. Meaning, so I started this work with a petrologist named Katie Chamberlain. She's in Liverpool, and she was very patient with me and teaching me the basics of geochemistry. And she was talking about interconnected systems. And after quite some time, I realized she was not we had something different in mind when talking about interconnected systems. She was talking about something chemical, and I was thinking about something physical. Interconnected must mean that the system has a tube connecting, hydraulic connection. But no, she was talking about the geochemistry. An interconnected system is a system where you see that the magma has been influenced by assimilation of host rock, mixing processes, some other magma that has entered the system, something like this. While isolated system means that the geochemistry in the magma chamber is only affected by the magma itself and nothing else, only what is contained there. So this would be chemically isolated and chemically interconnected. And this doesn't need to be physically interconnected or physically isolated. Physical isolation, chemical isolation, we came to the conclusion that chemical isolation must be a consequence, actually, sometimes, not always maybe, but often might be a consequence of magmas actually moving rapidly, because they don't give the time for the geochemistry to evolve. While interconnected means you actually are leaving the magma there for a while, or it moves so slowly that you give time to the magma to evolve geochemically. So, okay, so now I'm going to the open questions that I'm going to address today. So if really you have these interconnected systems, which is seen in rocks, in the petrology of rocks in many systems, how come that many of these systems actually erupt rarely? Because this is verified. Actually, isolated systems tend to erupt more rapidly, or tend to erupt more frequently, while interconnected systems tend to erupt more rarely. Why so? And this has something to do probably with this rapid ascent or stagnation that you can have in the magma. So what governs magma ascent speed and entrapment? If you look at the magma stalling in the crystal mash paradigm that has been forming in the last years through the work of Katie Cashman, Steve Sparks, and many big names in volcanology, what is written there is that the structure and the density and rheology gradients in the crust control magma stalling. So if you have a density layering or layers, they may help the magma just stall there. And then also the vagaries of geology, so the quirks, the weird things that you might have in geology, together with tectonic stress, may also influence this. And by the way, under fast rates of deformation, also the mash may fracture and allow fast rates of magma ascent. So what I'm going to do in this talk is actually to develop these 2 points, tectonic stress and rapid ascent by fracturing, because these two are things I've been working on, and I want to now see how they contribute. It's kind of a side thing in these papers on the mash, but I believe it's actually more important than what is commonly thought. And so this is what I'm going to develop today. So I will go through physical principles of magma ascent by diking. I will discuss applications to different tectonic settings, going through a little bit of the observations in the eruptive patterns, architecture of plumbing systems, and the compositions of the magmas and the gases, a very little bit. And then I will discuss the main points. So first of all, the physical principles. This is a picture of an fissure eruption that is driven by a dike. So it's a linear feature. Below you have a dike. Dike is a very thin magma field fracture. We know this because we see these things. And some colleagues think it's only a shallow thing. It's only from the magma chamber to the surface that we have dikes. But actually, in the Mayotte case, we saw that we can have easily some dikes going from the upper mantle to the crust in just one go. This one go will take maybe a week or two, but it can be very, very rapid ascent. So this definitely would be isolated ascent, isolated system, because the magma has no time to interact with anything. It will just come straight to the surface. How can this, I will explain you now what is the simplest model of isolated ascent for a dike. So here you see a column, a dike, and a column of magma, and then you have a column of rock just nearby. If magma is buoyant, the pressure inside the column will grow with depth more slowly than the pressure in the column of rock. This creates effectively a gradient of pressure or a change of pressure with depth that will effectively squeeze the dike from the bottom. Okay, so the fluid rearranges within the dike and you form a so-called teardrop shape, or it's only the cross-section. The dike is very long against the page, or Katie calls it carrot shape, also because this is orange. Anyway, just to remember, so this squeeze, what does it do to the dike? It creates a very inflated nose for the dike in the tip. The tip becomes swollen. Actually, it's very thin. It's not as fat as here in this figure. It's super thin. It's maybe 2-3 kilometers long and just a meter thick, so you have such a high stress concentration at the tip that the dike can easily fracture, cut through rock, even when the rock is very strong. Actually, it's easier for dikes to cut through strong rock than to weak rocks, by the way. And then the squeeze from the bottom will just push all the magma upward, and therefore the dike will maintain roughly the same mass, roughly will lose a little bit in the tail depending on viscosity up to the surface and can propagate this way quite easily. I will discuss how these dikes can be trapped. Okay, but before I do that, I need to explain you other things because they play a role. So the next thing I will explain is how dikes are oriented in the stress field. The stress field is responsible for steering dikes in the direction they go, plus buoyancy. Buoyancy, stress field. Okay, what about the stress field? The stress field represents, you have tectonic forces in the crust, lithosphere, and they might push and squeeze the rock in different directions. The principal stress axes here are the axes where you have the maximum stress and the minimum stress. So dike can, actually what direction they will use, they will open towards the direction where the compression is least. Okay, towards the axis of least compression, they will open because this is what easier. If you want to open in a direction, you choose the direction that is compressing the least. And this is usually roughly what dikes do. Faults are oriented differently, and that's why dike rarely take actually the pathway of pre-existing faults, because faults are optimized usually in the stress field to shear. They maximize shearing direction. Therefore, they are in the middle between the principal stresses because this is the maximum shear direction, roughly. Therefore, in the field, you can see that dikes and faults actually cross each other, like here in the Reykjanes Peninsula, where strike slip faults are oriented north-south, while fissures are oriented southwest-northeast. Why do we see this very easily in the Reykjanes Peninsula and not elsewhere? Because the Reykjanes Peninsula has a rather flat topography. I will show you now that when topography is not flat, directions are affected by the topography. So let's move now to this picture. This picture shows the Naples area. On the right-hand side, you see Mount Vesuvius. On the left-hand side, you see Campi Flegrei. These are two very different edifices from a morphological point of view. You have a cone, stratocone, and a caldera. If we look at the eruptive patterns, Mount Vesuvius erupts mostly from the summit or from fissure eruptions that are radially arranged around the cone. Campi Flegrei has no cone, has no summit which can focus eruptions, and the vents are scattered within the caldera. And actually, if you look at the fissure orientation, they are rather circumferential. They are not radial in the volcano. Why so? So let's focus now on what happens if you have a load. If you have a load, the load will attract dikes, as shown by these gelatin experiments and fluid injections in gelatin. So a small load will attract dikes, but they will also interact with each other and create this composite pictures. If the load is very large, if the volcano grows large, then you have all the dikes being focused by the volcano and being attracted by the volcano. By the way, the volcano also squeezes the tips of the dike from the top, because the stress that the volcano imposes on the crust grows as you go near to the volcano. Therefore, the dikes are squeezed from below and tend to ascend. At some point, they will be squeezed so much from the top that they cannot ascend anymore, and they will get arrested at a sweet spot where their buoyancy is matched by the load of the volcano, let's see, in simple terms. In these simple models, topography is just simulated by putting pressures on the surface. But if we create a gelatin model shaped as a volcano, we can also see what happens in the volcano if you inject the magma in the volcanic edifice, in the cone itself. And if we do this, how do I do this now? Okay. Then it's, sorry. Okay, then you see that dikes here in this gelatin edifice, they propagate radially and erupt on the flank of the volcano. Why do they do that? Because aligned with the summit of the cone, you have the strongest compression. On the flank of the cone, you have the weakest compression because it gently down the slopes, you know. So therefore, the squeeze, which for buoyancy works from the bottom to the top, within an edifice works from the side. There is more squeeze. There is more squeeze centrally, and this squeezes the dike laterally. So if you have both together, buoyancy and edifice, it may go oblique or lateral or up, depending on who wins. Okay, there is a competition between these two. There is a nice paper by Virginie Pinel and Catherine Meriot just out about this recently. Okay, so we have radial dikes in the edifice. What about a caldera? Here we have another experiment. I hope it's moving now, and then soon you will see a dike propagating. And actually, I would like to show you the whole experiment. I don't see the control on my video now because it's a new computer. Sorry. It may be because it's quick here. And then when you see here a negative topography, okay, like a caldera, a rift system, they have a negative topography. So what does the dike do when it starts to feel the stress induced by a negative topography? It does the opposite. If a topography focuses all the magma into the edifice, if you have a negative topography, you flip the stress axis, because you flip all the sign of the stresses, and then you deflect the dikes. They might erupt within the caldera if the caldera is shallow and wide, and they will erupt outside the caldera if the caldera is narrow and deep, like in this case. By the way, did you see that the dike slowed down? This is actually my main point today. When the trajectory is vertical, dikes take advantage of the full amount of buoyancy force because the squeeze is the most powerful that it can have. As the dikes gets tilted or even horizontal, the buoyancy force becomes less and less and less and less. And this leads to a slowing down of the dike. Then you also have additional stress contribution. So now I'm going to stop this and go ahead, but the dike will do this eventually. And we'll see a figure later. So in calderas, it might be more complicated than this. Actually, this is super simplified. For example, a caldera can have a resurgent dome. I mean, it can get quite complicated. But if the caldera is young, like Amphiphlegrae, the last caldera forming eruption was 15,000 years ago, then you might have a simpler case. Even here, there is a resurgent dome, by the way. So the decompression causes sills as the most favorable kind of arrangement below a caldera because you are flipping the axis and all the magma goes horizontal. And then when magma, it's actually rather hard to propagate magma from that position because you have a higher point in the caldera rims squeezing the tips of the dike. Okay, you have the dike. At the beginning is easy, but then as the dike reaches near the rims, it gets squeezed, and so it tends to open and inflate the center of the caldera rather than being able to propagate. Eventually, if it can, it goes sideways this way, and in spoons-like features, it embraces the caldera floor in this way. Like I put here for you to remember, like the petals of flower. Okay, so here we have a summary, like in an edifice, magma will be trapped below the edifice, possibly in a vertical kind of arrangement. Upon buildup of buoyancy, magma can escape, and then it would either erupt at the summit if it's lighter, or go down the flank of the volcano if it is heavier. In a caldera, magma ascending will be arranged as sills and then entrapped very strongly, maybe ascending again and be trapped in yet a new sill, and then only very rarely, because you can accumulate quite some magma here if the caldera floor is very large, like Yellowstone or big calderas, you can accumulate before it gets the power to ascend. And when it does, it's usually not at the center, but more towards the rim or even beyond the rim. So our main point today is, here I have a simple equation for the velocity of the dike by Davis et al. 2023, my ex-student, where this is nu is Poisson's ratio, mu rigidity, then you have V is the volume of the dike, eta is the viscosity of the magma, and then you have this delta gamma. This delta gamma for a buoyant ascent, vertical ascent, is delta rho G, the difference in density between the rock and the magma times the gravitational acceleration. Otherwise, you need to put the gradient of the edifice squeeze, like the height of the edifice over the radius of the edifice times rho G. You have to calculate what gradient is affecting your propagation and squeezing your dike. The main point here is that this is valid only for vertical ascent, but as a dike is tilted or even horizontal, the velocity of a tilted dike is just a fraction of the velocity, vertical velocity. It gets to half when it is 50 degrees the tilt, but if the tilt is 20 degrees, 10 degrees, the velocity can be even orders of magnitude less, 2, 3, or even 0. It can just stop ascending. So just one summary about this trapping. You can have vertical trapping when you have a loading above when you have an edifice above the dikes, or you can have horizontal trapping if you have a depression above the dikes. And now today, what I'm suggesting is that this is very effective in creating a potential for more mixing, more assimilation, creating an interconnected system, because you have that the dikes are trapped, the magma is trapped, there will be a chance to erode the country rock, there will be a chance for magma to be interconnected once they are trapped by either of these mechanisms. The vertical trapping is not as effective as horizontal trapping because upon build-up of buoyancy, they are already vertical. As soon as the magma is more buoyant, you can release it because this balance between load and buoyancy goes in the favor of buoyancy. In contrast, with calderas or rift systems, which also have a depression, just a long one, you don't have this possibility, because even if the magma gets more buoyant, it just needs to go horizontal and the buoyancy doesn't help very much. So horizontal trapping is very, very effective. And indeed, I believe that systems that have sills, they show the most interconnected geochemistry that we know usually. Okay, now I will go through some applications, and I start with volcanic arcs. And the volcanic arc that I'm going to start with is the Cascades arc. Here is a figure showing Mount St. Helens, a cross-section through Mount St. Helens. This is inversion of travel time data from P and S waves, and what they see is high density velocity, high density rigidity bodies below the main volcanoes. And also they see high VP over VS velocity, meaning that there might be some melt just below the volcanoes at more shallow depth. So they see magma chambers below the volcanoes and bodies with very high rigidity and density accumulated below. Well, not much in between. And then with a different technique, more reflection, seismics, one can see a lot of sills around. Here is Mount St. Helens in the middle here. And interestingly, these sills are mostly in the north. So basically, you see them more here in the north, in the south, to the east, to the west, but not really over Mount St. Helens. And so what they do is they basically create this summary where you have a lot of sills in the crust, below the moho, just away from the volcano, what I say, away from the topography, and just below the topography, you see vertical ascent pathways actually focused by the volcano. So if you go a bit wider, you will see that in the north, in the Cascades Arc, you have very linear feature with the volcanoes. Then you have a gap to the south of volcanoes. And then you have Mount St. Helens and Mount Adams. And then to the south, you get a lot of basaltic, even monogenetic vents, and a lot of magmas around the main volcanoes. There is a 2022 paper by Humphreys and Grinder, which shows, collects a lot of data and shows that what you have actually here in this segment is that the most compressive axis, in spite of it being a subduction, is not from the subduction, is not east-west, but it's actually north-south. There are many evidences for this, that the strongest compression is north-south, and that there is a gradient, so a change in the east-west stress as you go south. So in the north, you have compressional, east-west as well, not only north-south. In the Mount St. Helens segment, it's called the transitional, so you don't have actually a very weak east-west stresses. They may be flipped even during the seismic cycle, interestingly. If you go south, you know that actually it's extension, because there is a graben here, this red line. And then for these three cases, I did three very simple models where I added the topography with compression or more compression, less compression, extension. And they are a bit tiny, the figures, but I hope it's visible that if you apply, which is relevant for the gap, if you apply strong compression, magma pathways from anywhere, they will end up being horizontal. They cannot ascend. If you apply a weaker compression or a flipping compression, then the big topography of Mount St. Helens and Mount Adams are able to attract the magma, which will have actually a near horizontal path just below the volcanoes, and certainly had this other horizontal path in the past before the volcanoes were built. So therefore it's justified that there are sills everywhere in the crust, and the new trajectories are crossing these very old trajectories, remelting the magmas, having new very slow ascent, and then being focused just below where the ascent speed might a bit increased, but then you have the trapping of the volcano. So you see that there are several levels of complications in this stress. In the south, where you have extension, it makes sense that you have, in spite of the topography, or helped by the topography actually, a lot of monogenetic vents where the trajectories are separated, they ascend separated and erupt everywhere. They don't get focused. Now I will do application to continental rifts. So I take a risky approach and talk about the Massif Central and Limagne Graben. even if I know that, of course, you will know a lot more about that than me. Okay, so I took this from a paper I like very much from Michon and Merle in 2001, where they describe the phases of the volcanism there. So the first phase, pre-rift, the grabens were still not there. You have very scattered and few eruptions. Then there is a second phase where the graben starts to form, a rifting event, so-called, and then the events gets more focused in the middle of the rift. And then later, there is a major magmatic event in connection with the rift being very well developed. By the way, this pattern is not individual to the Limania Graben, but you have it in many rifts worldwide. It's discussed as being a universal pattern. So in a first phase, you have widespread volcanism, which if the rift is magma rich, is basalt floods. If the rift is magma poor, then you have individual scattered eruption. And then from scattered in rift, you go to off-rift volcanoes, actually. So you start to develop the vents shift completely and relatively suddenly to off-rift locations outside the graben in this pink phase. And during the same phase, you build the lower crustal sills, which are seen in the tomographies or in the seismics for all these systems. The controls of this are still debated. And regarding the petrology, you also see that laterally, centrally in the rift, where you also have calderas, the magmas become much more evolved and developed at 5-8 kilometers depth. They are associated with calderas or with shield complexes. While if you go laterally on the rift or even outside, then you get magmas that are generated from depth and come up relatively in one go, or they are relatively unevolved. So to model this, like I did for the arc volcanoes, here what I do is to consider, of course, in all cases, just the elastic layer, and then have the compression, which you can model with pressure sources pulling up. And then you need to have a developing graben. So you need to model the graben as becoming deeper and deeper and deeper. Usually grabens, they tend to, once at the beginning, maybe it's just a subsidence, which is widespread. And then after a while, you develop the faults. And once you have developed boundary faults, it tends to go deeper from there. In later stages, you may sediment the graben and have an imbalance of unloading and loading. So for this case, I produced figures that are different snapshots. So in these snapshots, you will see in the top part, the rift topography. So at the beginning is very flat. And these volcanoes are just the top of these trajectories. And the color here describes the orientation of the least compressive stress axis. So where you see one, dikes are forced to be horizontal in that, where you see dark colors. Dark will be forced to be horizontal. If it is light colors, dikes will be vertical because you have extension pulling, but then you have the decompression. They play against each other. So as you develop the rift topography, trajectories start to be more inclined, and they soon migrate rather quickly to off rift. And then you are starting to build a stress trap or stress barrier. Dikes tend to avoid it, or when they are born within the stress barrier, they tend to get trapped, and maybe they don't even ascend. Here I still didn't model the velocity. It's my next step. So in this situation, you would actually trap this magma. But if some can escape, then it will build an off-rift volcano, because you see all the vents get clustered just very thinly in just one region. So then if you trap the magma, it will slowly over long time manage from every seal. At some point you may create a new seal, but it will take a long time. So this will also offer opportunity for assimilation and for crossing with the other, new magmas and evolving the magma as well, until here is not really visible, but the very top, you see that here is white. Actually, the stress is such, it has a weird characteristic by which forces the dikes to be horizontal only within two depths. Above this other depth, the dikes are forced to be vertical, which is very weird in a way, but on the other hand, it fully corresponds to what we see, because we see in rifts, when they are mature and the magma is in the middle of the rift and we see it, the dikes are vertical and they are born out of sills that are just below, and then they become, you have a sill, maybe 10 kilometers depth, and from that sill you see a dike going laterally like this. This is consistent with this stress field. If you also add the stress interaction between the dikes, then you see that if you use a Macaferri model, just to be clear for who knows it, then you see that the dikes cross each other, interact. Some of them, so first are in rift, then they go off rift, and then as you go up and up, then you end up having eruptions within the rift by these dikes. So now I reached the conclusion. If you do very simple elastic stress models, I tell you, it's really, really simple, transparent from a point of view, oversimplified from another point of view. But it is, if you keep things this simple, they are really simple to do. They already give you a lot of insight on what you can expect from the trajectories of the magma. And I plan to also, in connection with the new Encyclopedia of Volcanoes that is going to come out, I plan to have exercise and scripts so that anyone can do this. Anyone can model these kind of things, because they are quite effective in reproducing observations of magma trajectories. They lead to stress traps. Stress traps can be vertical or horizontal, and they provide an opportunity for rock assimilation and interaction between successive magma batches. And they may work simultaneously at different levels of the magma system. First, you may have sills, then you may have vertical trapping, and your edifice may come and go, become a caldera, become an edifice, blah, blah, blah. So it becomes a really rich world. Which I think this considering stress, gives a very important contribution to both geophysics and geochemistry. Thank you for listening.